Hello students, so today we will discuss about uh, resonant tunneling devices. In short, RTD. Now, although resonant tunneling devices were not the first category of solid-state non-electronic device, we explain their operation in detail first because it illustrates energy quantization and tunneling in the simplest form. So, energy quantization and tunneling in the simplest form are explained in these devices. Now, it is crucial to the operation of these RTDs and other categories of non-electronic devices that the energy of the quantum states in the potential well on the island can be adjusted relative to the energy of the bands in the source and drain. Now, an example of this is can be seen in the following diagram. Like if we have an island here, and we have the barriers here, and so you can take. So this is the island. I call it as I. These are the barriers. Call it B. This we take as the source, and this we take as the drain, and we have metal contacts at these two sides. These are the metal contacts, and Me. Now the barriers create a potential well around the island. So this is the potential well created by the barriers. And they usually prevent charge from flowing through the device. So charge is basically due to the formation of these barriers, charge flow is restrained. Now increasing the bias shifts down the energy. Now we increase the bias. What it will do, it will shift down the energy. That means you can see a shifting down of the energy, and all the states in the well, and brings them into resonance with the mobile electrons in the occupied conduction band. So there are some mobile electrons in the conduction band. What the increasing the bias it will do, it will make a resonance of the energies of the states in resonance with the mobile electrons in the occupied energy band. That means those energies or the energies of those electrons which are traveling, they are at resonance. So that is why we can see a tunneling. So first of all, there is a resonance taking place of the electrons in the already existing conduction band and the mobile electrons, and due to this resonance we get a tunneling. That is why the name resonant tunneling diode. So this is where the electrons are transmitted. And so this is the occupied conduction band, and increasing the bias towards energy, and this is how the electrons are transmitted. Now, similar adjustment of energy levels in the potential well relative to those in the source can be achieved by varying the voltage on a third terminal, that is the gate, rather than the voltage on the source. So instead of increasing the bias at the source, what we can do, we can change the bias at the gate. So it will look something like this. We have gate electrode here, and we have non-metal contacts here. These are the metal contacts, and this is the gate electrode, and this is the Allen. And these are the tunnel barriers. And this is the electron channel. This is the electron channel, or the channel through which the electron flows. So this will also create a potential will something like this. Sorry. Now, what we are doing here, we are increasing the bias at the gate. So increasing the bias at the gate will again cause shifting down of the energy level, and this will eventually cause transmission of electrons through tunneling. So this is the occupied energy levels, and it will get transmitted due to this potential at the base, at the gate. So this is actually called, instead of resonant tunneling diodes, since they have three terminals, source, gate, and transistor, it is called the resonant tunneling transistors. Or you can call it as RTT. Now this RTT can perform both as switch and as an amplifier, as in MOSFET. Perform both as a switch and as an amplifier, like a MOSFET. Actually, this nanometer scale quantum effect devices, such as these, can have switching operations that are superior to those in the case of MOSFETs, and can have multiple on and off states associated with multiple discrete quantum level inside the potential well, if these levels are widely spaced enough. These multiple on and off state are illustrated in this, for example, in in a device like this, that you have a gate here. This is a gate, SG, and we have small RTDs. So these are small resonating turning diodes. This is the source, and this is the drain, and you have a gate oxide here. So the nano devices having multiple of these RTD and RTTs can have multiple on and off state. Like in this case, it can have a potential barrier like this, and if you plot the corresponding current voltage plot, so it will, so this is for an RTD, and let me try it once again. So we draw the current voltage plot for an RTD, for an quantum dot, and for a single electron transistor. Then three of them will show different characteristics. For an RTD, it will be like this. For a quantum dot, it will be step function, and for a single electron transistor, it will be a step function but in a different time. So this value, this corresponds to the delta E in the case of RTD, whereas in the case of quantum dot, the delta E is this much, whereas in this case you have a value called U in the case of a single electron transistor.